Hi everyone, this is Ruijie from Ruijie. Today I'm very glad to introduce our SIGIR paper, MetaHKG Learning for Few-Shot Temporal Reasoning. And this is a collaborative work with my lab members from Ruijie, Yutong Zhang from Stanford University, and Shengzhong Liu from Shanghai Jiao Tong University. In today's world, we are surrounded by numerous news articles describing what's happening around us. So temporal knowledge graphs are therefore proposed to organize such time-varying events. I'm not sure the expertise of the audience, but the temporal knowledge graph can be viewed as a set of quadruples, including the triple subject relation object associated with specific time steps. And the reasoning on temporal knowledge graphs aims to predict the recent and future events based on the historical observations to automatically update the temporal knowledge graph to capture the most recent information. And it can be widely utilized in multiple downstream scenarios, such as recommendation, social event forecasting, and some information retrieval applications. One unique property for the temporal knowledge graph is that we observe the new entities continuously appearing on the temporal graph. For example, it could be a new politician in a geopolitical temporal knowledge graph, or some new users or new posts on a social-centric temporal knowledge graph. And moreover, we find on a famous temporal knowledge graph wiki, more than 60% of entities are new nodes that firstly appear in the last 1/4 of the time steps. So one direct question that motivates our research is, can we directly utilize the existing reasoning method, mostly for embedding methods on the new entities to facilitate their reasoning performance? But the question is unfortunately no, because we also observe that, as shown in this two figures below, new entities are usually initially associated with a few amount of links. Take the wiki as another example. We find that on average, only 1.5 events are associated with the newly appearing events in the first time step. So it motivates us to study the following research question, that is a few-shot representation learning on the temporal knowledge graphs that aims to learn the representations for newly emerging entities based on extremely limited observations on the temporal knowledge graph. And we hope it can facilitate some downstream applications such as future event prediction. So what types of characteristics of the new entities can motivate the model design? I'm going to talk about the two properties. The first is so-called exponential growth. We find that as time goes by, the amount of entities in the temporal knowledge graph grows exponentially over time. It indicates that maybe we can select a latent space that has a large capacity to learn the discriminative representations and avoid the representation collision. And secondly, we observe a clear power law distribution for the amount of events associated with each newly appearing entities, and also it follows a clear hierarchical structure. In the figure on the right side, we find that first of all, the entities follow a structure, a hierarchical structure, and the new entities shown in the blue tends to lay at the outer side of these hierarchies. So it indicates that we can select a latent geometry that is good at capturing such a power law distribution and the hierarchical structure. Combining the two, in this paper, we aim to learn a hyperbolic few-shot representation for newly emerging entities based on the extremely limited observations for temporal graphs. Towards this goal, there are still two challenges remaining. The first is how to design operations in a hyperbolic space to represent the graph. And the second is how can we design an optimization strategy to effectively generalize the existing model to new entities with observation of a few-shot events. Our solution is called MetaHKG. It is a meta-learning framework to enable few-shot temporal reasoning within a hyperbolic space. The key design consists of two parts. The first is the representation learning in one type of hyperbolic space called Poincare ball space. And another is our optimization strategy called meta-hyperbolic learning. And I will introduce them respectively. First of all, we aim to learn a time-evolving representation for the entities over time. And our intuition is that such a representation dynamics is caused by the changes of temporal neighbors that entities will engage at each time. So our encoding module first sample a dynamic temporal neighbor set over time. And then we attentively integrate the information from the temporal neighbors to form the time-evolving representations. And the tricky thing here is how to achieve this goal in the hyperbolic space. So we propose a corresponding attentive aggregation and the attention weights considering the node feature, entity feature, relation feature, and the time feature within the Poincare space. One thing to mention here is about the time encoding. For time encoding, we want to maintain a property so-called translation invariance. That is, one pair of two temporal points with the same time delay should have the same effects. So we prove that our proposed method can maintain such a translation invariance. So any two time points with the same time delay should have the same effects on the final attentive weights. The next question is how can we design an optimization strategy to enable smooth adaptation of the new entities from the existing method. Here, I'd like to briefly introduce a background of meta-learning. So basically, meta-learning is a proposal to extract the generalizable knowledge from a set of related tasks, so that once we have the same related new task, we can easily generalize our knowledge from the existing task to the new task. In this exemplary figure, we show that how the meta-learning works for a text image classification task. And based on that, the support set and the query set concept are proposed to denote the training samples and the testing samples. Following the similar intuition in this temporal knowledge graph concept, our motivation is that from the existing entity, we can use sufficient information to train a global parameter as a form of global knowledge. And then we can easily borrow it from the existing entities to the new entities. And here we formalize the knowledge as the model's capability to sample and aggregate information from the temporal neighbors. Specifically, we empirically find that a set of global parameters that is not quite sensitive to the entity selection, we formulate it as a global parameter, including the relation embedding, time embedding, and the trainable creatures to customize the hyperbolic space. And then the entity embeddings and the specific attention parameters to parameterize the aggregation and the sample strategy can be viewed as an entity-specific parameter. So our optimization strategy is shown as this figure. We propose basically it's same as a model agnostic meta-learning. It consists of a bi-level optimization. For the inner loop optimization, it mimics the fine-tuning process that given a good enough global parameter, we can fine-tune the parameter into entity-specific one. And also it includes another layer of outer layer optimization that can constantly improve the initialization of global knowledge. So we first use the initialization to train on the existing entities by iteratively optimize the inner loop and the outer loop optimization. After the meta training, we can achieve a good enough global parameters so that we can directly inherit that global parameters on the newly emerging entities and just use the few short observations to enable lightweight model fine-tuning. And finally, we can use the fine-tune the entity-specific parameters for the reasoning in the future. Empirically, we evaluate our method on 3 commonly used dataset. As we can see, we want to highlight that we observe the events happening in the first and the first 5 time steps associated with each entity is quite low, from 1 to 5, indicates the practical value of our method. And and another thing is we follow the common few shot cycling. That is, we assume we can only observe the first k, like 1, 2, 3 events of each new entities, and we use a ranking-based metrics to evaluate our method. Compared with base size from multiple related areas, such as knowledge graph embedding, few shot knowledge graph embedding, we can observe a consistent improvement on all cyclings on 3 different data sets. More importantly, we want to show the advantages of our solution compared with Euclidean counterparts. First, we find that a hyperbolic solution requires a lower dimension of representations to achieve the similar level of prediction accuracy. And also, we find that the hyperbolic operation can help to stabilize the training process for the outer loop optimization because of the easier model adaptation. And this is achieved by the geometric property of the hyperbolic space. And also, I'm going to show some temporal reasoning results on this task. And we find that our model can achieve improvement for both the new to existing type of event and the new to new type of events. And more improvement comes actually from the new to new prediction, and illustrating our ability for the new entity reasoning. And also, our prediction can achieve a constant improvement over time, although we can only observe like the first 1 event for each new entities. And also, application studies shows that our optimization strategy is the best compared with some naive fine-tuning, model agnostic meta-learning, and the global meta-learning that does not distinguish from global parameters and entity-specific parameters. And also, this experiment can show the effect of the time encoding. Basically, we find that with the fixed time encoding, it can hurt the performance a bit. So to summarize a little bit, in this paper, we study a few-shot temporal reasoning problem that aims to represent the newly emerging entities into a hyperbolic space and facilitate the future reasoning performance. Okay. And we propose a MetaHKG framework to better model the new entities, and the empirical results show the effectiveness of the proposed framework. And this work also opens several potential opportunities for future extension. For example, first, as we all know, the geometry of representations includes multiple types of geometry, like the spherical, Euclidean, and hyperbolic. So we can achieve a self-adaptive geometry learning selection. And also, with the recent advance of large language models, probably we can extend this few-shot learning task to a more practical zero-shot learning task, where in that setting, the language could be another media to transfer the generalizable knowledge from the existing ones to the newly emerging ones. Okay, I would stop here, and I'm glad to take any questions from the audience. Thank you.